what are series exactly?
It's the sum of the sequences?
It's the sum of the terms in the sequence. So that's really all a series is going to be, is add up all of the terms in the sequence, and you now get a series. So there's two different situations here. One, for a sequence to converge, that just means that by the time you get to the nth term, the infinity term, you see that it is getting, that the final term is getting close to a fixed number. That's different than saying that a series converges. In order for a series to converge, it means that when you add up all of the numbers in a sequence here, the final result of that sum goes to a fixed number. And so it's a big difference between a series and a sequence. A sequence is just the list of terms. The series is when you add up each of those terms. And so we just want to look at the notation of what series look like. This is, of course, our summation symbol, which means to add up. This n equals 1 tells you which term to start with, so start with A1. And this top number here, in this case infinity, means to keep adding numbers all the way out to infinity. If I only wanted to find a partial sum, then I might make that infinity equal to a 5. And then I'm only finding A1 plus A2 plus A3 plus A4 plus A5. Okay? So now we're going to take a look at a couple of really important sequences as we move through, or series as we move through here. First one is just a very simple one. Let's just say that A sub n is equal to n. Then the sum from n equals 1 to infinity of n means nothing more than plug in 1 to n, plug in 2 to n, plug in 3 to n, plug in 4 to n, and add them all up. And so what do we notice about this series? Well, the series just keeps getting larger and larger and larger. It doesn't approach some fixed number, which is why this series is considered divergent. Let's look at another sequence, or another series. This is going to be a really important type of series right here, but we're going to look at the sequence of 1 over 2 to the n. Again, that just means that when I plug in 1, 2, 3, 4, and 5, I'm just getting various powers of 2 in the denominator. But notice that the numerator is staying as 1. So I should realize that the terms in the sequence are going to what? So what is the limit as n approaches infinity of A sub n? Ideas? Nobody. Okay, well, what is A sub n? A sub n is the sequence. Limit as n approaches infinity of 1 over 2 to the n. Anyone now?
Is approaching 0.
0. Doesn't it look like the terms are getting closer and closer to 0? So the limit of the sequence is 0, going from 1/2 to 1/4 to 1/8 to 1/16 to 1/32 to 1/256 to 1 over 4096, right? Notice those terms are just even getting smaller and smaller because the denominator is getting larger and larger. All right. But that's a lot different than the limit of the sum. If I were to take a look over here and say, what's the limit as n approaches infinity of the sum from n equals 1 to, I mean, I guess that we should probably relabel this as I equals 1 to n of a of 1 over 2 to the I. All I've done
Isn't this
here
an
is
integral?
well, yeah, and that's the deal here, is that we're looking at this and saying, well, isn't that what we did for an integral? This took the limit of the sum as we added up a massive number of rectangles? And the answer would be yes, if it was a function. This is not a continuous function, though, remember. This is just a collection of individual points. So all we're doing when we're taking the limit of the sum is saying when I add up each of these heights, basically, then what number does it actually approach? So notice why I changed this this limit, or I'm sorry, this index right here to an I. It's because what's happening here is I'm plugging in 1 to I, 2 to I, I'm plugging in 3 for I, 4 for I, 5 for I, all the way to n. So the final term would be 1 over 2 to the n. Now I'm saying, let's take the limit as this n value goes to infinity. So I'm forcing the numerator, not the numerator, the upper limit to go to infinity. And so I had to just change the variable inside of this sequence. But either way, when I end up looking at this now, it turns out that this limit of the sum, and we can see why in a few minutes here, but this limit turns out to be 1. Turns out that if I add 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, and I add up an infinite number of terms, that is going to sum to 1. Each partial sum gets closer and closer to 1. It'll never exceed 1. It'll just get closer to 1. And now I'd like you to realize the big difference between a sequence and a series. So limits of sequences are just saying, what does the final term seem to get closer to? While the series is saying, what do all of the terms seem to add up to? So any confusion on that? Okay, cool. Well, we're just going to look at a couple of what we call partial sums. We refer to partial sums by the letter S, capital S. And so S3 would just mean add up the first 3 terms. Sn would mean add up the first n terms. And so if the sequence of partial sums here is convergent, okay, then the whole sum is convergent. So essentially, if I could see that by adding the first, or by just putting the first term, and then coming up with a second term, which is the sum of the first 2, and then come up with a third term that's the sum of the first 3, and then the sum of the first 4. If I try to actually look at how those sums are approaching a fixed number, if it appears that each of those individual sums approach a fixed number, then I could say that the series is convergent. Okay? If it doesn't happen, then obviously the series is divergent. So let's just take a look at this one right here. So this example is a really cool one because this is an example of what we refer to as a telescoping series. There was a Khan Academy video that talked about something like this before as well, but this is a telescoping series. And so if I just wanted to determine whether or not this series converges or diverges, I want you to really realize as well, most of the time when we ask, does a series converge or diverge? The answer is either yes or no. We're not being asked to say, if it converges, what does it converge to? Because most of the time, we'll have no idea what it converges to. All we're going to be able to prove is that a series converges to something specific. There's only a couple of types of series where you can actually see what the series is going to be, okay? And so, anyhow, so there's, like I said, there's two different types of, well, a few different types of series where you can actually determine what it converges to, but most of the time you would just say either yes, it converges or no, it doesn't. All right, so if I were to just keep this in the form, if I were to just keep this in the original form right here by plugging in some numbers here, then notice that plugging in 1 would make this 1, and therefore I would get ln of 2 plus. Then if I plug in 2, I would get 1 plus 1/2, which would be ln of 3/2 plus. Then I would plug in 3, and I would get ln of 4/3 plus. And then I would just keep going on with this. Now it's a little tough for me to tell whether or not that converges or not, because I could see that 3/2 and 4/3 are getting smaller and smaller and smaller. So by the time I end up getting to some fixed value, maybe this sum is getting closer to some fixed number. I don't know. So instead of writing it like that, we end up writing it by creating one fraction perhaps. So sometimes just doing a little bit of algebra can help us to come up with what the sequence is. All right, but if we do that, then it turns out that ln of n plus 1 over n is going to give me basically the same terms that I just saw right here. So that also didn't really help to determine what's happening to each term. But because it's a logarithm of a quotient, I could apply the quotient rule by just separating the argument by subtraction. So what if I were to rewrite this sequence as a difference? Well, anytime you could write it as a difference, not anytime, but a lot of times, telescoping series occur when you see a difference. Now I'm going to put difference in quotes to help you to realize that we're talking about the answer and subtraction here when we say difference. So if we were to write this as ln of n plus 1 minus ln of n, now notice what each of these terms do. First one is ln of 2 minus ln of 1. All right, plus. Now we move up again. So now we plug in 2 and we get ln of 3 minus ln of 2. Now we keep going. ln of 4 minus ln of 3. Then we go to the next one, ln of 4 minus, or ln of 5 minus ln of 4. And at first glance, you might not necessarily see why this was such a big deal. But if I just look at A1, ln of 2 minus ln of 1 is just ln of 2. So to find S2, that just means let's add together the first two terms. S3 means add together the first three terms. S4 means add together the first four terms. So look at what happens as we do this. When I end up seeing the first two terms, notice how ln of 2 and negative ln of 2 cancel. So that means that the second term here, or the second partial sum, is the natural log of 3. But then let's add one more term. And if I add one more term, notice by adding the next term, the ln of 3 minus ln 3 cancels. So all we're left with is ln of 4. And then if I go on and on and on and on and on, the ln of 4 would cancel. And then in the next term, ln of 5 would cancel. And then in the next term, ln of 6 and ln of 7 and ln of 8. So notice that all that's going to be left by the very end is going to be the partial sum of ln of n plus 1. So what this is converging, in quotes, or diverging to is going to be whatever happens when n approaches infinity. So we could see that the sum will become infinity, which is why we say that this series diverges. So the reason this is called a telescoping series, anybody seen, like, in a naval movie or something like that, to where they've got these telescopes where they take it out and they extend it outwards, right, so that it all kind of compacts into itself, and then they pull it outward to make it look longer. Well, that's basically what's happening in a telescoping series, is that as you keep adding more and more terms, certain terms cancel, and then these terms cancel, and then these terms cancel, and then these terms cancel. And so what ends up happening here is that you compact it down to the first term and whatever happens at the last term as well. Okay, that's one type of series. But that one doesn't show up too often. I want to talk about one that, there are a couple of things that are important here. This, I might as well talk about it now. It's going to be in 5.3, but it's on this slide, so I might as well just mention a couple of these important ideas. So if a series is convergent, then that must mean that the sequence has to go to 0. I want you to think about that for a few seconds here. If the series converges to a fixed number, meaning if I add up all of the terms of the sequence and it converges to a fixed number, then that must mean that the sequence went to 0. Why is that? Why can't the sequence go to 1 and the series diverge or converge?
Because if the sequence went to a non-1 number, then the series would keep going up.
Yeah, because I would just keep adding bigger and bigger and bigger, adding numbers over and over and over. So eventually I would just keep adding a string of ones, which would go to infinity. The only way for the series to possibly converge is if the limit of the sequence goes to 0. Because what that would mean is that each of the terms eventually becomes so small that they become insignificant in the sum. So it's important to recognize that if the series is convergent, then that must mean that the limit of the sequence is 0. However, the converse of this theorem is absolutely false. Let's think about why. Let's say that I know that a limit goes to 0. The limit of a sequence goes to 0. So each of the terms eventually approach 0. What does that tell me about the series? Nothing. It means that it could converge or it could diverge. And we're going to see a couple. I saw you just had some videos last night, one of them being what we call the harmonic series and the P series, where sometimes the terms just keep getting smaller and smaller and smaller. But sometimes when you add those terms up, it goes to a fixed number. Sometimes when you add the terms up, it diverges to infinity. So basically what we're saying is the only way to be convergent is if the terms go to 0. But just because the terms go to 0 doesn't mean that it converges. And that's basically what we get for this test for divergence. Okay? So the test for divergence is a really simple test to apply, and you should always apply it first. So if what you're trying to do is determine does a series converge or diverge, is a very simple test to determine if it diverges. If you look at the limit of the sequence and it either doesn't exist or it doesn't equal 0, then the series is absolutely divergent. So let me say that again. If you try the limit of the sequence and it doesn't go to 0, then the series is automatically going to diverge. And that's basically kind of obvious from this theorem up here. The only way for a series to converge is if the terms in the sequence go to 0. So if the terms in the sequence don't go to 0, then the series is automatically divergent. Okay, that's what we call the test for divergence. And it's just a good starting point to test for convergence and divergence of any series. Okay. Pretty cool on that. Now, as a corollary to that, if we find that the limit goes to 0, if you try this test and you see, oh, the limit of the sequence goes to 0, then you still have no idea what to do. Okay, so there's still no saying whether or not it converges or diverges. Well, we learned some ways to find limits in Calculus 1. We're going to use a lot of those same tools in Calc 2 and dealing with series. So if I want to find this limit as n approaches infinity, notice that this gives me infinity over infinity. And we know that's indeterminate form. It doesn't mean that it has no limit. It just means it's indeterminate form. So what we could do is we could divide every term by the highest power term in the denominator. So we just divide every term by n squared. And notice that we now get 1 on top, and on bottom we get 5 plus 4 over n squared. Now, if I were to take the limit as n approaches infinity, the only place to plug in infinity is here. And any constant over infinity goes to 0, so my answer is 1/5. Now let's think about what that means. It means that I'm trying to find whether or not the series converges. Whether the series converges. If I take all of the terms, as I start plugging in 1, then 2, then 3, then 4, then 5, and so on, I want to determine whether or not the terms in that sequence go to 0. Well, it turns out that they didn't. The terms went to 1/5. So if all the terms go to 1/5, that should mean that eventually, like 10 billion terms down the line, I'll just be keeping, or I'll just continue to add things that are really close to 1/5. And if I just keep adding things that are close to 1/5, notice that it's impossible for this to ever converge to a fixed number because it'll just keep getting larger. And that is the key to the test for divergence. We basically said, if I want to determine whether or not the series is convergent, then all I need to do, right up here, if I want to determine if this series right here is convergent or divergent, take the limit of the sequence. And if the limit of the sequence doesn't equal 0, then it's automatically divergent. So this should be the first thing you do. What we're doing in this whole chapter is determine whether series are convergent or divergent. This should be the first thing we do every time. Let me rephrase that. This should be the first thing to try every time. Taking the limit of the sequence is sometimes difficult, so we bypass it. But it's if you could take the limit of the sequence pretty easily, then you can see that this is a pretty helpful tool, okay? But it doesn't mean that you necessarily need to apply this test every time, because sometimes taking the limit of the inside or taking the limit of the sequence is a challenge, okay? All right, well, the last thing I want to talk about here is geometric series. Okay, I'm not going to go through the proof of this because the proof was described on the video last night. So what I would encourage you to do is to watch the video on this. Okay, but a geometric series is a really important type of series here. It's a series that looks like this. Now, more specifically, keep in mind that for a series, n is the only variable. So for example, you might see the sum from n equals 1 to infinity of 2, which would be a, times 1/3 to the n minus 1. That would be a geometric series. What makes a geometric series geometric is that you see some base to the power of n. So if you ever see a fixed constant to the nth power, that's automatically a geometric series. And the cool thing about geometric series is that they have particular sums. So sometimes these will converge, and we can see really easily if they do converge. And sometimes they'll diverge, and we can see really easily if they diverge, simply based off of the value of r. So r is the common ratio that every term multiplies by to get to the next term. Okay, so for instance, I'm just going to go ahead and come up with a few of these. Let's plug in 1 here, right here. If I plug in 1, then I get the answer of 2. If I plug in 2, I get 2 times 1/3, which is 2/3. If I plug in 3, I get 2 times 1/9, which is 2/9. If I plug in 4, I get 2 times 1/27, which is 2/27. And so what we should recognize about these is that these terms seem to be getting closer and closer to 0. So what does that tell us about the series?
Convergence.
Tells us that it does one or the other. Just because these terms go to 0 doesn't mean we automatically know it converges. We still have to go through some other process here to be able to do so. So that was what we mentioned right up top here. We said that if the sequence is non-zero, then we know it automatically diverges. But if the sequence equals 0, right, if the limit of the sequence equals 0, we still don't know whether it converges or diverges. But what we do know about geometric series is that it actually always does converge in certain criteria. So if the common ratio is a fraction between -1 and 1, then not only do we know that this series right here converges, But it also turns out that we know exactly what it converges to. It converges to this number. It's actually pretty crazy because most sequences or most series that we determine converge, most of the time we're not able to find what it converges to. We just know it's going to get close to some number. I don't know what it is. I can't prove what the number is, but I know it's going to get close to a number. But with geometric series, we actually can compute what it gets close to. And I encourage you to go through the proof on that video this evening or before you do your homework. Okay? So I'll just keep that on there. That's important. All right, well, I want to just demonstrate by this graph then why this works. Maybe I won't. Give me a minute here. I think it might be on the sequences one. Yeah, it's on this one. So r to the power of n. So now we know that this right here is considered a geometric sequence. Okay, geometric. And we want to see why it's convergent. If it's convergent here, if the r value is between 0 and 1, or -1 and 1, but it's divergent everywhere else. So I kind of want to look at this sequence a little bit closer here. And I'd like to realize that if r is bigger than 1, maybe like 2, okay, then let's think about 2 to the power of n. Well, that's going to be these yellow dots right here, okay? If I keep plugging in numbers, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, notice that these numbers just keep getting larger. So that's why I can see automatically that if r is greater than 1, the sequence goes to infinity. So that one's pretty obvious. I can see that the same thing is going to happen if r is less than 1, okay? Because if r is less than 1, like maybe we have -2 to the power of n. Now look at what's going to happen. If I plug in 1, I get -2. Plug in 2, you get +4. Plug in 3, you get -8. Plug in 4, you get +16. So in this situation over here, if r is less than -1, then that just means that it jumps from positive to negative to positive to negative, but it just keeps bouncing back and forth, but still going off to infinity. Plug in 3, it's going down here. Plug in 4, it's further away. So that should be obvious as to why if r is less than, that should be -1, if r is less than -1. So if r is less than -1, then this diverges to infinity as well. So now we should probably look at -1 and 1 individually, okay? So what if we have the sequence 1 to the n? Well, now we would be saying 1, 1, 1, 1, 1, 1. Well, you can see that if r is equal to 1, it obviously converges to 1. That's really uninteresting, right? So notice that if r is equal to 1, it definitely converges to 1, which is why there's an equal sign right here at 1. Okay? Let's take a look at if this was -1 though. What if r was -1? Well, that would mean if I plug in 1, I get -1. Plug in 2, I get 1. Plug in 3, I get -1. Plug in 1, I get... So you can see that this right here is what we referred to as our alternating series. It just jumps back and forth from -1 to 1. Okay? From -1 to +1, to -1 to +1, to -1 to +1. So it's not converging to any fixed number, which is why we could see if r is equal to -1, it doesn't work, which is why down here, right there, there's no equal sign at -1. But now for the most important values here. What about values that are less than 1? Well, now if I see something like, I don't know, 1/3 to the power of n, notice that now when I plug in 1, I get 1/3, then a third of that, then a third of that, and a third of that, and a third of that, and a third of that. Notice that each of these are in fact converging to 0. So if I see any fraction between 0 and 1, it's going to converge to 0. But even if this was a negative, that would converge to 0 as well. Plug in 1, you get negative 1/3, then positive 1/9, then negative 1/27, then positive 1/81, then negative 1/243, positive 1/729. And they just keep bouncing back and forth, but they still converge to 0. So that's why what's most important here about all of our geometric series is that they converge when the R value is less than 1. So if I were to say the sum from n equals 1 to infinity of 3 to the nth power, does that converge or diverge?
Diverge.
It diverges because R is greater than 1. But what about this one? Now it converges because R is less than 1. But what about this one? Still converges because R is in the range from -1 to 1. So this is a geometric series, and it turns out that these are really important and, in fact, really helpful. Okay, I could say that this converges since R is between -1 and 1. Okay. Geometric series pop up all the time, but sometimes we have to do a little algebra to see that this, that a particular sequence does fit that pattern. Okay. So just make sure that you recognize that when you're dealing with a geometric series, that you're looking at your particular terms there and seeing what the R value is. So I want to just look at this sum right here. So here's a sum that I didn't know what the formula was. So the first thing was to come up with a sequence here. Okay. So the first thing I might recognize is that in order to get from 5 to -10/3, I multiplied by -2/3. Now that starts to indicate that maybe this is a geometric series, but it's only a geometric series if I can keep multiplying by the same exact number to get to the next terms in the sequence. And sure enough, if I multiply each of those terms by -2/3, I get a fixed R value, a fixed common ratio. So the first thing that I would do here is I would say, well, I think that this is then the sum from n equals 1 to infinity of -2/3 to the n. But notice that that's not quite going to be true, because if I plug in 1 here, notice that gives me -2/3. And I'm not supposed to get -2/3. So that's why subtracting 1 from the exponent turns this exponent, when I plug in 1, into a 0. And -2/3 to the 0 power is 1. Getting closer, but notice the first term is not supposed to be 1, it's supposed to be 5, which is why I multiply by 5. And now that's exactly the form that we learned on the prior slide that says that the standard form of a geometric series is A times R to the power of n-1. Well, does this converge or does it diverge then? How do we know if this converges or diverges?
If R is between -1 and 1.
Yeah, notice that -2/3 is in fact between -1 and 1. So I know that it converges. But we just learned that not only do we know that this geometric series converges, but we also know what it converges to. It converges to A divided by 1 minus the common ratio. So if I plug that in, I get 5 divided by 1 plus 2/3, which is 5/3. And therefore, all of these terms will converge to 3. And that would be our answer. So geometric series right now are about the only types of series that we're able to find the physical sum. Most of the time, all we can say is it converges or it diverges. But this one we know converges, and we know what it converges to.